Hi there, David here. I've been working on the design and construction of a pendulum clock for some time now. So let me show you what I've been up to. So the concept for the clock was to have an open clock face, so the inner workings are visible, with both the hour hand and the minute hand sitting on the same arbor as is normal, driven by their respective gearing. All of that driven by great wheel down below with its hanging weight, and then two-step reduction to get to the second hand. So the one reduction, two reductions to the second hand, which is sitting on the escapement wheel with some sort of escapement mechanism sitting up on top. I wanted something more advanced than the simple anchor type escapement, and in the end I decided on the Harrison twin pivot, which has two extra arms sitting on the pallet frame, which engage with the escapement. So that was the concept, and then of course working out the details from a blank sheet of paper is what comes next. So after I'd got the concept laid out, some simple hand sketches. This, and then leading into some block sketches just done on a spreadsheet, and that was sufficient to get me far enough to be able to start working on the frame. At this point I didn't know the exact details of how the Harrison twin pivot was going to work and how much space it was going to require up here at the top, so I just made the frame a little bit longer than necessary with a view to cutting it down to size once I had all the details worked out. So that let me start construction of the frame and also of these gears, and I wanted to cut the main gear train by hand, again just to experience doing that and to see how difficult that was and how possible it was to make gears that ran properly by hand. And as for the materials, well, I've got some birch left over, so I'll use that for the frame and for the pendulum stick, and then I'm going to cut the gears out of this black acrylic sheet that I have. So here are some of the materials and components that I needed for this project. So we've got the weight for the pendulum, the aneroid cells to do the air pressure compensation together with various weights that will go with them, a pendulum bulb which has now been split in half, BBs for weight in the pendulum bulb and in the driving weight, various clicks and click springs and ratchet wheels and springs for the maintaining power wheel, various set screws that I needed, some acrylic tube for the air temperature compensation, and various options on the spring that the pendulum hangs from, and various bearings. And here's a list of where I got those supplies. So here's an online animation of the Harrison twin pivot escapement, which shows you what I'm shooting at. So there's a pallet frame at the top with two pallets, which alternatively engage on the escapement wheel. And as the pendulum swings, each pallet arm swings in and catches on an escapement tooth. And then when the next when the next pallet swings in, it actually pushes the escapement wheel backwards slightly, which causes the previous one to release. Fortunately, I found this paper online which explains how the twin pivot works and how to lay it out. So it takes you through all of the geometry of the escapement, explains all the various components, and then after all of that you get down into the equations to calculate all those different angles and spans. So I took all of that and dropped it into a spreadsheet, and that let me play around with the various parameters that can be varied to come up with a design that I liked and which worked with the frame layout that I had. That approach also let me validate the movement of the pallet arms and the pallet frame against the escapement wheel for correct engagement. And here are the various inputs that I've chosen to use and the results from the calculations. So having got all the defined angles and all the locations for all the key points, the next problem was to work out the shape of the pallet frame and the pallet arms that would actually work and engage properly. And I laid this all out in cardboard just so that I could quickly make different shapes and see how they worked. So I knew these were the points for the pallet frame. Here's the defined swing for the pendulum, so I know how far that's going to go. And the question is, what shape is going to get me to the escapement wheel without causing clashing on the other components? So I played around with various components here just to see what would work. Gradually refining that until eventually I got to the shape that I've adopted, which is this one on this side. And same thing on the right, working through different shapes until I got to something that works. So as the pendulum swings, this one over here engages, pendulum swings back, it all slides out of the way until the one on the left engages on the next tooth. So here's the process that I've been using to make the gears. I'll have to show you on some pieces of scrap and extra gears that I've got, because all the main gears are now made and in the clock. So start off with printing off a template and adhering that to the material that I'm going to use. The first step is to drill out the center hole. Here's the circle jig on the bandsaw with a different piece of material. So I advance the jig until we get to the center line of the circle, lock it in place and then rotate to make the cut. And then it's back to the drill press, and with the center point located and held, rotating around and drilling out each of these gullies between the gear teeth. You can see I've drilled all of these out. With hindsight, I would make these gullies deeper and slightly wider to give greater clearance with all the gear teeth when we get to meshing into its partner pinion. And after that, it's over to the scroll saw. And now I'm going to use this vintage scroll saw to cut out the rest of the profile of the gear teeth. And that gives me the full profile of the gear teeth, rough cut. I've left them slightly away from the line. I'll bring them to the line with a sander. And then we're back to the bandsaw, this time with a sanding belt installed and a simple platen at the back to support the belt. I'm deliberately leaving the teeth just a little bit long. I'll bring them to the correct radius on the next step. Next step is to use the circle jig on the disc on the belt sander. Advance the gear until it just touches the disc, rotate it, and that'll bring all the teeth to exactly the same radius. continue the process in all the steps, then you end up with a complete gear wheel. So it's not particularly quick, but it does certainly appear possible to produce some decent looking gear teeth by hand. This is a depthing gauge that I made, which lets me check the spacing of the arbors to get correct engagement of the different gear wheels. I can slide the piece on the left in and out to increase and decrease the spacing of the arbors until I get something that works properly. This is one of the gearing pairs. There are 3 pairs like this in the clock, and now you can see that this engages quite nicely. I then replaced the short pieces of arbor with some other ones that had pointed ends and used those to mark the exact positions in the frame of where I needed the pivots to be. Because of the way the escapement works, the distance between the teeth is critical. As the pendulum swings, the new pallet has to nicely swing in and just catch the tip of the tooth. So the spacing between the teeth on the right side and the tooth on the left side, that's 8 teeth away. That spacing has to be precise and consistent for all the different gear teeth. So here I am using the depthing gauge again to measure the spacing from a reference point on the right side against the brass pin to a reference point on the left side, 8 teeth away. Doesn't really matter where the reference point is. What's critical is that those distances shouldn't vary. After I had checked all the distances, there was a surprising amount of variation, more than I was expecting. It turns out that the laser printer that I had used to print off the original pattern isn't quite true, and circles aren't circles, they're slightly oval. And that was why I had a cyclical variation in the distances on the teeth. So now I had to repair that somehow. After 4 rounds of measuring and fine filing on certain teeth to optimize the distances, 4 rounds of that got me to a much better consistency. We're down from an error of 3 millimeters, more than 3 millimeters from the biggest spacing to the smallest. Now the error is down, the difference is only 0.3 of a millimeter, so it's much improved. So the pinions are just a push fit onto the shaft, and there's enough friction there that works. The wheels, however, the plastic is too slippery and the fit is not tight enough. So when the pinion turns, the gear wheel doesn't turn with it. So I'm going to fix that by pinning through from the wheel into the collar. That'll also keep, the collar will also keep the gear wheel truly perpendicular to the shaft, and hopefully that'll eliminate some of the wobbling problems that I've had. So the wall of this collar is 1/8 of an inch, which gives me just enough room to drill a 1/16 of an inch hole. Now that the collar's drilled, I've got the escapement wheel sitting on a piece of the same shaft as its arbor, and the collar's sitting down on top of the escapement wheel, and I can drill through the collar and through the escapement wheel, and that'll then accept a pin to keep the two located together. So here's the little pin that stakes the collar to the wheel. The pin actually has a little bend in it so that it's a push fit in the hole. and that just keeps those two staked together. The friction fit of the pinions on their arbors works for the rest of them, but it's insufficiently rigid for the first pinion, accepting the load coming in from the great wheel and the weight on the barrel. So I'm going to drill it and install a set screw to keep it more firmly attached to the arbor. The borehole of the bearing is supposed to be the same as the outside diameter of the shaft material, but actually they aren't, and the bearing is too tight on the shaft and jams, doesn't fit on properly. So here I am just adjusting the outside diameter of the shaft until the bearing slides to where I need it. I needed to cut a cylinder for the barrel that the weight is suspended from, but I don't have a lathe, so I had to find a different way of doing that. And here's what I did. I made a jig for the table saw with a small block mounted in the jig that can rotate. And you see here I've made some passes over the table saw initially just to remove some of the bulk material. And then to finish it up and turn it into a cylinder, I just rotate the block over the top of the blade as it advances over the top of the blade, and that cuts it to a cylinder. And here it is after it's been drilled to reduce some of the weight. And here's the pendulum that I'm using, that I'm hoping will be sufficient to give me reasonable accuracy on the timekeeping. At the bottom, I've got the bulb with the coarse adjustment on the rating, and temperature compensation in the barrel here. Further up, we've got fine adjustment on the back, and then aneroid cells to compensate for changes in air pressure. And up at the top, we've got interchangeable suspension cheeks to compensate for circular error, and the whole thing is hung on a traditional suspension spring. So this is pendulum number 4, so we'll see how this one works and whether the various compensations are sufficient to do the job. One of the features of this twin pivot escapement is that it always has to be under power. If at any point there is no power being delivered to the escapement wheel, then there is no friction keeping the pallet engaged, and there's a risk of both pallets disengaging and then the whole gear train running out of control until the weight hits the ground. Now, of course, normally there is power driven by the weight, except when the clock is being rewound. And for those few seconds when you're rewinding the clock, then there's no power being delivered to the escapement wheel because the weight is being lifted. Harrison devised a way of dealing with that problem about maintaining power. Effectively, you have a weight-driven clock driving a spring-driven clock. So down here at the bottom, the weight hanging on the barrel drives this wheel, and then from this wheel there's a spring that drives the first of the gears. And during rewind, this wheel locks, and it's the spring that continues to drive this first great gear wheel. So at this point, I had had enough of cutting gears by hand, and I didn't really want to cut this one, which has 240 teeth. Didn't fancy doing that by hand. So I redid the whole thing in CAD, which meant I had to choose a CAD program to start with and then learn how to use it. Drew the whole thing up in CAD, drew up this wheel, as well as the the 4 smaller gears here for the motion works to convert from the minutes to the hours. And for good measure, I added in the hour hand, the minute hand, and the second hand, and sent all of that off to a laser cutting service. And in the space of a week, they came back all beautifully cut, far more accurate than I could do. So that's clearly the way to go in the future, is just to draw it all up in CAD and not mess around with a whole lot of hand filing of gear wheels. So we're now at this stage where all the components are made, but they're not quite functioning just exactly as they need to. I've got some troubleshooting to do. In particular, there's a little binding on the gears. So just on some of these engagements there, you can just about see that the bottom of the tip of tooth 5 is hitting the bottom of the gully between 25 and 26. So it needs a little adjustment to increase the depth of the gully on some of this engagement. Also up here on the pallet arms. The pallet arms are hung on bearings mounted in the back, and the bearings actually have a little bit of a wobble to them. So when this tries to engage, there's a wobble to it, so it may or may not engage properly. So I need to change out the bearing for one that has less play in it. Down at the bottom, I've got the click for the maintaining power wheel. That click, again, any slight wobble on the wheel on its shaft will lead to that click disengaging. So I need to come up with a mechanism to make sure that that click stays engaged, and also to properly sight and locate the click spring. I did also notice that the single stack of aneroid cells that do the air pressure compensation can cause a twisting motion in the pendulum if the correcting mass is large, because the aneroid cells are sitting in front of the plane of the pendulum swing. So I'll change those out for a pair mounted each side of the pendulum rod, and hopefully that will correct that problem. I'll also make them a stack of 4 instead of a stack of 2, and that greater sensitivity will reduce the amount of mass that's required to achieve compensation. And also, now that the whole mechanism has been established, I can go ahead and reduce the height of the top of the frame. This section up here can come down to be in line with the back support. I think that's enough for this video. I'll deal with troubleshooting those problems and hopefully getting the clock to a point where it's ready for startup. I'll deal with that in the next one. Thanks for watching.